Hi, in this section we are discussing intrinsic semiconductor. We shall take the most common case of germanium and silicon whose lattice structure as shown in the figure. These structures are called the diamond-like structures. Each atom is surrounded by four nearest neighbors. We know that silicon and germanium have four valence electrons in its crystalline structure. Every silicon or germanium atom tends to share one of its four valence electrons with each of its four nearest neighbor atoms, and also to take share of one electron from each such neighbor. These shared electrons pairs are referred to as forming a covalent bond or simply a valence bond. The two shared electrons can be assumed to shuttle back and forth between the associated atoms, holding them together strongly. Figure 14.4 schematically shows that the two-dimensional representation of silicon or germanium structure shown in this figure, which overemphasize the covalent bond. It shows an idealized picture in which no bonds are broken, all bonds are intact. Such a situation arises at low temperatures. As the temperature increases, more thermal energy becomes available to these electrons, and some of these electrons may break away, becoming free electrons contributing to conduction. The thermal energy effectively ionizes only a few atoms in the crystalline lattice and creates a vacancy in the bond as shown in the figure. The neighborhood from which the free electron with charge minus q has come out leaves a vacancy with an effective charge plus q. This vacancy with the effective positive electronic charge is called a hole. A hole behaves as an apparent free particle with effective positive charge. In intrinsic semiconductors, the number of free electrons Ne is equal to the number of holes Nh, that is Ne is equal to Nh is equal to Ni, where Ni is called the intrinsic carrier concentration.